Hi, I am Vaibhav. Today we will be discussing about Zephyr architecture and interrupts involved in it. So, before we go ahead and jump into the interrupts, it's important to discuss and mention what actually is Zephyr. So, Zephyr is a real-time operating system which is open source. The kernel based in Zephyr is a small footprint kernel. The intention of basically building a small footprint kernel is to embed the kernel and run it properly inside the resource constrained devices like embedded devices, IoT devices, and devices like dark variables. So going ahead, as part of this presentation, I'll be mentioning about a very high level detailed understanding about the kernel involved in Zephyr and the tasks and threads which are running inside the Zephyr. Before we actually jump into interrupt, it is important to understand how interrupts are basically running in the conventional and traditional Linux architecture, so that we can actually compare the differences and the similarities between the two. So going ahead, so these are the features which Zephyr as a real-time operating system supports as far as interrupts are concerned. So when we talk about interrupts, there has to be something which has to be interrupted. So when the kernel is already up and running, it is important for us to have some processes already running or threads. So as part of Zephyr, we have two different kinds of kernel, which are microkernel and nanokernel. So why do we have two different kinds of kernels? So as we already know that Zephyr is already intended for resource constant devices, microkernel comes into picture when these devices are not bounded by memory. They are having good amount of memory and they can support a heavy kernel. So microkernel will be having applications which are not resource constrained when compared to nanokernel. So nanokernel is a kernel which requires a very high performance computing. When I say high performance, it doesn't require high level of device architecture, but it just requires lesser memory and computation. So when we have two different kinds of kernel, we are having two different kinds of contexts. So one is task and one is thread. So task context is the context which we discuss when we are having microkernel into picture. So as part of task context, it is preemptible context, which means a different task can come and preempt the kernel. As part of nanokernel context, since we already discussed, the threads or processes running inside nanokernel have to get finished as soon as possible. It is non-preemptible. So when we are having both of these tasks or processes running inside the Zephyr's kernel, it is important to understand that they can be interrupted in the case of hardware signals to CPU. So what is an interrupt? So before we get into the question of interrupt, we should be understanding what new things Zephyr has brought into the picture and what are the differences Zephyr has in comparison with the already existing Linux architecture. So as part of Zephyr architecture, we are having task and fiber as we have already discussed, and I would like to mention that both task and fibers can be interrupted by Zephyr interrupts. Going ahead, we are having something called nested interrupts. So nested interrupts are nothing but when a high priority interrupt comes into picture, it can preempt a lower priority interrupt and come into the execution. When the execution of high priority interrupt is over, a lower priority interrupt which was preempted can come back to execution and start the execution. As part of Zephyr, we have fibers and tasks as we have already discussed, and the interrupt service routine can mark both fiber and task as runnable. And as we already know, there are three contexts: task context, fiber context, and interrupt context. So interrupt context always takes priority over task and fiber context. So as you already know, there is something called exceptions in all the architecture. So as part of Zephyr architecture, we are having exception number 1 to 15, of which exception number 7 to 10 and 13 are reserved, which would mean there would be no existing handler for these exception numbers. For all other exception numbers from 1 to 15, we are having all the handlers, and Zephyr has already dedicated purpose for these exceptions. For example, exception number 1 is used for reset and it's used for system initialization. Likewise, exception number 11 is for context switch, and it is already registered handler is present inside the kernel. Now, like I had mentioned before, we'll be having a short discussion about what is IRQ and what is a shared IRQ. Why would we actually need a shared IRQ? So, when a hardware sends a signal to CPU, CPU drops from whatever it is doing, if it is not an interrupt handling what it is doing, and interrupt signal comes into picture and a new process starts executing. This new process is nothing but interrupt service routine, ISR. So, like I said, an interrupt comes from hardware more often than not, and if this interrupt is coming from hardware, we need to have hardware lines which are called interrupt lines on the hardware. So if you imagine that way, a number of interrupt line can limit the number of devices which can cause interrupt, which should not be the case, because otherwise we can have only so much devices to be handled for interrupts. So to solve that purpose, we are having something called shared IQs. So what actually shared IQ does? Shared IQ takes an interrupt handler and asks, can I share your interrupt handler and IQ line with other handlers? Well, when such a request comes into picture, there are two checks which kernel does. First, if this new ISR request is a new request. If it is a new request, we will handle a new ISR request and the flag should be set to share. Second, if there are already existing handlers, we will be checking if those existing handlers have actually enabled the interrupt sharing or not. If the interrupt sharing is enabled, we are good to go, and this new request for the handler also gets added to the shared IRQ handlers. So this is how actually a normal Linux and conventional Unix architecture supports interrupts from very high level of understanding. In Zephyr, we can have interrupt service routines which can be made and built and installed in a static and also in a dynamic way. Now it's important to understand that Zephyr has a monolithic kernel, which means when we want to make and develop an application for Zephyr, we want to develop an application image which boots up when you boot the kernel. So everything is interlinked. So you have to make a decision of whether your interrupt has to be a static interrupt or a dynamic interrupt. So static interrupt is the interrupt which we make when the build flags and build parameters are already known during the build time. And thereafter we come into the picture of a dynamic interrupt, and apart from that, I'll be discussing about static and dynamic interrupt in the next slide. It's important to mention this, that interrupt service routine can also be written in assembly language, which is not always the case in all the other Linux kernels. So Zephyr kernel can support wholly developed interrupt handler in C or its assembly language too. So as part of static and dynamic ISR registration, I had already mentioned that one depends on build time availability, and second comes up when kernel is up and running and the parameters are known then. So for static registration, we use, to configure the interrupts, we use IRQ underscore config macro and IRQ underscore enable handler to start and configure the interrupts. For a dynamic registration, we use both of them, and also we use IRQ connect handler. Apart from that, there is one important thing to note. When you register a static ISR, it cannot be uninstalled in a static way, or by default it will never get uninstalled. So what you have to actually do is you will have to have another dynamic ISR which will be uninstalling the static ISR. This also is the case with another dynamic ISR. So when you have another dynamic ISR of which parameters are known on the runtime and the interrupt has come, to uninstall this ISR, you will have to make another dynamic ISR to get rid of the existing ISRs, the requested one. So to disable the ISR, we are using IRQ disable API, which is already also an existing API as part of Zephyr kernel. So now at this point of time, we know how to install, how to disable the interrupts in Zephyr, and at this point of time I would like to discuss more about what we have done as part of the project. So our project required us to make a device driver for HCSR ultrasonic sensors. So this sensor, HCSR sensor, has a purpose of calculating the distance. This distance is calculated based on the trigger which a echo pin receives. So there are two pins, trigger and echo, and based on the trigger, based on the interrupt received by one of the pins, we calculate the distance, the pulse width. So as I mentioned, we are depending on the pins. We have to enable the interrupt on a particular pin so that when that pin is triggered, we get an interrupt and the interrupt service routine gets handled. To serve that purpose, we are using GPIO pins to connect HCSR chip, HCSR sensor. So when we have the connections in place, we will want to enable this particular pin to call the ISR handler. For that purpose, GPIO functionality in Zephyr already has APIs for GPIO callback functions. So what is a callback function? So callback function is a function which we are having, so we can understand in a very similar fashion of ISR handler. It's just that there are different APIs what GPIO library is providing to us. So as part of that, to initialize the callback function, we are using GPIO init callback, which is already also an existing API. So the very first parameter which it takes is GPIO callback structure. So GPIO callback structure is used to register a device instance callback. And this is very important to note at this point of time that GPIO callback structure should always be having a global presence. Because if it is defined in a stack comes and goes, but interrupt can happen at any point of time. So we want this GPIO callback structure to be declared globally so that we can use it at any point of time. Going ahead, like we can have multiple ISR and multiple IQ handlers in case of conventional Linux. We can have multiple callback functions in case of Zephyr architecture, and they can actually share the IQ functions. It is important that all the GPIO callbacks should be pointing to a unique structure. That is very important to note. So all the callbacks should necessarily be a unique pointer to a GPIO callback structure, like I have already mentioned. It should be noted that finally the callback can be added using GPIO add callback API. So at this point of time, we have configured the API. We have defined what structure we are going to use, a unique pointer to the GPIO callback structure, but we haven't actually added the callback. So add callback is used by providing your device data structure as the first parameter to the API, and second is the callback structure which you had already mentioned. When the callback has been added, now at this point of time you have to enable on a certain pin. So when a certain pin has been triggered, a callback should come into picture and a callback handler should be executed. This is achieved by having GPIO pin enable callback API, as part of which second parameter goes as a GPIO pin number. So this is what we had used in case of our assignment, wherein we have provided GPIO pin number. So on this pin number, sensor was installed. When our sensor was getting distance measurement, we were calculating the distance based on the callback structure handler. So as part of GPIO enable callback function, we have enabled the callback on a specific pin. To disable the interrupt pin, we are using GPIO disable callback function. It is very important to clear the data structure and clear the callback functions after you are done with the application performance. At this point of time, I would also want to discuss, like in conventional Linux, we are having something called bottom halves and top halves. So essentially what is important to understand here is interrupt has preempted many other processing tasks. So it is important for interrupt to exit the processor as soon as possible. So keeping a lot of execution and executable statements inside interrupt handler is not a good practice. So what we do is we offload task to another process which we call bottom halves. That is how it works in conventional Linux. In case of Zephyr, what we have is we can offload the functionality of so for example, in the case of incomplete ISR logic, the kernel synchronization can hand off the task to task or fibers in case of micro or nano kernels. This can be seen as top and bottom half functionality in case of traditional Linux. So microkernel provides task IRQ objects. These task IRQ objects are used to streamline the handoff process of remaining tasks of the callback or of the IRQ handler to another processes. Each task IRQ has a unique and number identifier, and this can range from 0 to n minus 1, where n is the total number of IRQs in the system. Other important ISR handlers to note at this point of time are ISR event send. So if there is an event, for example in this case ISR event signal, we are having key press as the event. When the key is pressed, an IRQ, an interrupt is registered, so interrupt is called. So to send a signal to the ISR routine, we are using ISR event signal. And other important ISR handlers are ISR send, give and take, which are used for taking semaphore logs from the ISR routine, ISR context. And when we are executing a task, when we are in task context and interrupt has come, we can get the task priority using ISR task priority get. So this is all from my side, and this was a very quick introduction of Zephyr, a bit of detailed explanation of IRQs in Zephyr and how they compare and differ from the existing Linux architecture. Thank you.